we've seen some practical examples of using Prolog, but how does it actually work and how do we implement it? To look at that, I have to talk a little bit about the theory behind Prolog. The first interesting thing in Prolog is what's the model of knowledge behind it? When you write some programs, what does it actually mean? Prolog makes this thing called the closed world assumptions, and this means that only the declared facts are true. So if you have a model of a family tree in Prolog, there are no unknown children. Everything that's there in your definition that exists and nothing else exists. The important consequence of this is that it shapes how Prolog represents truth and false. So negation in Prolog is a tricky subject, and we will not really be getting into the details in TinyProlog. But if you have truth, if you derive something in Prolog, it means that it's provably true. So I can find some assignment for the variables, that's the evidence that something holds. But if you want to represent that something, if you want to represent falsehood in Prolog, then the typical representation of that in Prolog is that it corresponds to something not being provably true. So falsehood is you cannot prove that something is true. And that's different from proving that something is not true. So not isn't a negation that you can work with directly. Not is something that works a bit on the meta level by saying, I cannot prove this. So this is something that is legitimate assumption in this closed world knowledge model, where if I cannot prove something is true, it is false. But if you were to represent partial knowledge in some sense in Prolog, this wouldn't work as easily. In Prolog, how do we actually represent programs? So Prolog programs are there's two things. At the program level, you can have rules and facts. And a fact is just a clause that has only a head. There's some definition like human Socrates. That's a fact. And then you can have rules which consist of head and body, where the head is one clause, one term, such as mortal of X. And then the body is a sequence of terms that define what has to hold for this to be derivable. So if you say mortal X is implied by human X, then that is a rule, that's a derivation rule. So we have facts and rules. The rules consist of head and body. The facts only have head. And inside these things, we have terms such as human Socrates, mortal X, or human X. And those can consist of three things. They can be predicates, it looks like a function call, it's sort of saying, I have some predicate with some arguments. So that's one syntactic structure. Another is an atom. That's the names with the lowercase starting letter. This is representing some specific entity. And then we have variables which start with uppercase letters. There's more theory behind Prolog, because Prolog programs are represented as logic clauses, and they use this particular format that's called the horn clause. And this is basically an implication where conjunction of all the clauses or all the predicates in the, or the terms in the body implies the head. So you can read this as a logical implication, and this also means that it's equivalent to a disjunction where you negate all the elements in the body. And when we run a Prolog program, what happens behind the scene is something called the SLD resolution. And this is a decision procedure for logic terms that are using this particular horn clause representation. And the two important properties of the SLD resolution is that it's sound and complete. That means when it gives you a result, it really is the correct result. And if there is a result, it will find it. Or in other words, if there is no result, it will tell you that there is no result, and it will be the case. So this is a fully decidable procedure. I need to look a little bit at the variables in Prolog clauses. So when you have a Prolog derivation, Prolog formula, the variables that you use, they're universally quantified over the whole formula, but then existentially quantified over a body. If we say that x is a grandparent of y, if there is a parent of y, z, and a parent of zx, this really means we're saying that for all x and y, there exists some z such that z is the link between the two people. And if you apply the usual logic operations to this, you can see what this corresponds to. If we rewrite it as disjunction, and then it really becomes universally quantified over all the variables with the negation of the parts of the body. The one practical consequence for our implementation of this is that when we are applying a rule, because these rules are universally quantified, we will need to rename the variable names. Because when we pick one of those rules, if we just use it with the variables as they are directly named in the program, we could have a name clash when we use the same grandparent operation multiple times. So that's one practical thing that we will have to be mindful about. The next thing to look at is how does this resolution actually work? So we will look at the individual steps of this in our implementation, and there it will make more sense. But the idea is that the user writes a query. This is what we wrote in the terminal, and what sort of starts the Prolog search. And this can be a single or multiple terms with some variables. So we have this query as the starting point, and then what we do is that we let's say it's just a single term. So what we do is that we find an applicable rule or fact that matches this term. And what we have to do here is we go over all the terms and we try to use unification, just like what we did when we were unifying types, to find a rule or a fact that can be unified with the query. And if we find one, then this unification will generate a substitution or a variable assignment. We keep the variable the assignment, and then we go over the body of this rule and add all the terms from this body to our list of things that we still have to resolve. And we keep applying the substitution, keep repeating our search until we solve all the goals. So let me try to show you how this works, at least in a very high level way. So my example is again the family tree, and I have two rules that define a parent. So we have Charles and his two parents, Philip and Elizabeth, and then I have some rules here that define that Philip is a male and Elizabeth is a female. And then I have one rule here that says the mother of Y is a parent of Y who is also a female. And so if we get a query that's asking who's the mother of Charles, so I'm going to say mother X of Charles. So this is the initial prompt, initial query that we get from the user. Now, what we do then is that we go over all the facts and rules in our database, and we find one that can be unified with the query. So this happens to be this rule, and if we do, and what we do then is that we do a unification of the query. So that's what the user gives us, and the head of the rule. So we try to unify mother X Charles with mother X Y. And as I said before, we have to be careful about the variables, because the X and Y in the mother, we have to come up with some new names to avoid clashes. So what we do is that this does actually unify, and we will come up with a unification that says this X that came from the user is going to be some X1. I'm just adding 1 to all the variable names from the mother rule, and then I will infer another part of the substitution, which is that Charles will be unified with this Y1. So once we've done this, we go over the body, that's parent XY female X, and we add those things to our list of things that we have to solve. So I'm going to say parent, and now here I have my X1, and for Y I'm going to substitute Charles. Well, for X I have to substitute as well. So for X1 I substitute X, and for Y1 I substitute Charles. So that's one more goal to solve, and another goal to solve is female, and here I will need X. So how do we do that? Well, we continue and we look at our facts about parents and see if we can find one that we can use. So the first one that we could possibly use is just the first one from the list. And if we try to do this, we can unify parent X Charles with parent Philip Charles, and this will give us an assignment for X, which is Philip. And then we can go with this. You can see that this is not going to work, but we can continue with this and say, okay, well, if X is Philip, then now what we have here is that we need to find, after this substitution, we need to find female Philip, and we continue and go through all our facts, and we find no fact that can be unified with this, so this approach fails. So we then go back, we use backtracking, and we return to the step 2 and take a different path, pick the next rule from our database, which is parent Elizabeth Charles. from this, we get, I'm going to make it clear that this was a failure. We get x equals Elizabeth. We apply this substitution to the pending remaining goals in our list, and we get female Elizabeth. And now we go over the list of facts, and we do find a matching fact that we can unify with this, and then that's a success. And the result of running this program is this assignment that X is Elizabeth. So that's how the SLD resolution works using a very small example. There are two more smaller technical things that I would like to talk about. The first was the numbers. So as you saw in the earlier demo, numbers are a little tricky in Prolog because Prolog doesn't automatically do the actual evaluation. The basic encoding of numbers in Prolog is that you can do something like the piano arithmetic and represent number using an atom representing 0 and a predicate representing a successor. So a number 3 is then a successor of a successor of a successor of a 0. And this is something that we will use in our TinyProlog. Real-world Prolog systems don't do this. They use various extensions to the basic constraint logic programming paradigm. In Prolog, there's a support for, or it's implementing constraint logic programming CLP with Z, with numbers, and that's extending the basic logic programming solver with a specialized solver for integers. There's a bunch of other solvers added in Prolog for Booleans and for other types of numbers. The other interesting technical detail in Prolog is occurs check. So we had this in TinyML, where we wanted to make sure that you never unify a type variable with a type that includes the same variable. And in Prolog, there's an interesting thing happening because Prolog does not do this by default. So in Prolog, you can actually define a variable a that is f of a. There's an option to enable occurs check. That's what we implemented in TinyML. And if you turn this on, then a term like this will be rejected. Many operations in Prolog are implemented in a way that they support what Prolog calls rational trees or cyclic terms. So if you have this variable that is defined in terms of itself, a lot of terms will actually work and they will not get stuck. They will not run into an infinite loop. And the reason why Prolog does this is that not doing the occurs check, not making this check, makes the resolution much faster. So it's faster, but it's not quite right, and you can optionally turn it on. So there's some interesting operations that do fail when you don't enable occurs check. There's an operation to turn it on using the set Prolog flag predicate. So let me show you how this actually works. So one interesting thing that you can define is that you can actually say a equals a, let's do 1 plus a. And this is just defining a as 1 plus a. And Prolog will happily accept this, even though it doesn't really make much sense. And you can do a lot of things with this. You can kind of create a list of a's, you can reverse a list that contains multiple a's, and so on. So the fact that it's self-referential doesn't cause a problem immediately. But if we say b is a, then this is going to fail, because what we are now trying to do is that we are trying to force the evaluation of A, and this cannot be done because it's cyclic. So if we then define Prolog flag occurs check true, if we turn this checking on and we enter the same term, A equals 1 plus A, then it just says false. It doesn't even let us define the term. So this is an interesting extra thing that you can implement in your TinyProlog later on.